Welcome back to chemistry class. Today's learning objective is about the complex compounds. Already the complex compound we have started, and previous class I have explained you about the isomerism of the compounds. These complex compounds. As we know, the complex compounds are the compounds where a central metal atom and the ligand are bonded together through a coordinate covalent bond, and these doesn't lose the properties even on they don't lose their identity even in the solution. They don't break down into simpler ions. These have high stability even on dissolving, and their properties are different from that of constituents or complex compounds. Now we'll see the isomerism. In isomerism, compounds having same formula but different in the structural arrangement or three-dimensional arrangements are isomers. Coming to the isomerism, structural isomerism, and stereoisomerism. In structural isomerism, I have explained about the ionization, hydration isomerism, and linkage isomerism, coordination position isomerism, and polymerization isomerism. Coming to the stereoisomerism, there are two types. In the stereoisomerism, compounds which have same formula but differ in the spatial arrangement is stereoisomerism. And in stereoisomerism, isomers with same molecular formula but ligands occupy different position are geometrical. Now, what is the second type? Stereoisomerism. Optical isomerism is a second type of isomerism. So, compounds having same formula and same physical chemical properties but differ in rotating the plane polarized light are optical isomers. Compounds having same molecular formula and same physical chemical properties but they differ in rotating the plane polarized light are known as optical isomers. And this phenomenon is optical isomerism. So, optical isomerism, you should know before what is this plane polarized light. What here is instrumentation. Optical isomers, they have opposite effects on the plane polarized light. No superimposable mirror is formed. Here you can see this is the ordinary light before polarization. And after polarizing, passing through the polarizing filter, it gets polarized and it's moving only in one direction. It has the electrical, here you can see these components here. It's focusing in all sides, and after passing through the polarizing filter, it's passing only through single direction, that is plane polarized light. And in this plane polarized light, if our sample is enclosed in the tube and this plane polarized light is passed through the sample tube, you can see there is rotation of plane polarized light either in left side or the right side. So depending upon the rotation of the lights, if it's from right to left, if it moves towards the right, then that clockwise, and that is D compound, D isomer. If it is rotated in the left side, then that is L isomer. See, you can see the mirror image of the right hand and the hand. Once if you put the left hand, that becomes a mirror image, and that is right. And optical isomers can be observed in the octahedral complex ions. optical isomerism you can see in the octahedral complex ions. So here you're having cobalt, your tetramine. This is the coordination number is 6. There are 2 chlorines. This is cis isomer. Chlorines are side to side, same side. So it is cis. And this is trans. Sorry, this is also cis and cis. Both of them here you can observe this are facing opposite. This is the mirror image. Now this is another. So it is not as the same. Now coming to this compounds, chlorines are on opposite side. This is trans. Cobalt, ethylene, diamine, dichloro. That is the cis compound if 2 chlorines are same side. And once if you put the mirror, they are the mirror images. Yeah. And coming to the trans, these are the mirror images. So this is the optical isomers in the octahedral complex. This is isomer 1, mirror image. Here, this is the isomer 1, mirror image. Yeah, this is isomer 2. So the trans isomer, its mirror image are identical. They're not the isomers of each other. Yeah, they are mirror images, but they're not isomers. And coming to this one 2, that is trans. Isomer 2 cannot be superimposed exactly on isomer 1. They are not identical. Once if you see the bonding in the octahedral complexes, your chromium hexamine complex, 6 ammonias occupying the empty orbitals, and thereby chromium hexamine complex is formed. Similarly, hybrid orbitals, if you see square planar here, 3 empty, we need 4, and it's getting jumped into the electron, and you get 4 and dsp2 square planar complex, tetracyanonyl complex. And we'll see the hybrid orbitals in the tetrahedral. Here, zinc tetrahedral complex. It needs 4 hydroxyl molecules to bond, and in order to bond, it needs 4 empty orbitals. Here, 4 empty orbitals. sp3 is a hybridization, and you get sp3 hybrid orbitals here, tetrahedral arrangement. Now we'll see how the bonding takes place. I'm going to explain you the hybrid orbitals bonding basing on the crystal field theory. So the isomerism I've seen, optical isomers D and L. Now I'm going to explain you hybridization in the octahedral complexes. We have seen how these are formed. The complexes, the hybrid complexes here, hybrid orbitals, and the bonding in the square planar complexes, and the tetrahedron. And I'm going to explain you about the crystal field theory. We'll focus on the energies of the d orbitals. I'm going to explain you the crystal field theory, and based on this theory, hybrid orbitals and bonding in tetrahedral, square planar, octahedral will be explained. First, assumptions, we'll see here the ligand, it's a negatively charged. Negatively charges. The ligands are the negative point charges. Metal ligand bonding, it's completely ionic. If it is strong field, low spin complex, you get large splitting is observed at d orbitals. If it is weak field, high spin and small splitting is there in the d orbitals. Okay, now d orbitals in the octahedral field of the ligands, you can see we have dxy, dxz, dyz, xy, xz, and yz. There are 6 ligands in the octahedral complex. There are 6 ligands in the octahedral complexes. And how they approach in the, we'll see. The dxy, you can see the orbitals in between the axis. You can see dxy orbital, the ligands there. Here d orbitals. D, this is the y axis, and this is the x-axis, and this is the z-axis. Here you can see dxy, between x and y, you're having the lobes. Electrons are revolving between the lobes. xz, between the z and x, the orbitals are here. You can see the electrons are rotating in between the orbitals. And dyz, between the y and z axis, these lobes. Here, the electron clouds are concentrated. The electrons are moving in between these two axes. And coming to the dx square, y square, and dz square, the electrons are moving along the axis. Moving along the axis. So, once if you see splitting of the d orbitals in the octahedral complex, 3d orbitals, this is the central metal ion, 3d orbitals, all these are the degenerate orbitals. As I've told you, these 5d orbitals, these are in between the axis and these are along the axis orbitals. And 3d orbitals in the free ion state. Once if the ligands are approaching nearby, the energies are raised. You can see this is the energy coordinate. 3d orbitals in the free ions are on the, when before the ligand approaching, they are in the degenerate state. Degenerate state, almost same energy. And as the ligands are approaching, the energy of the d orbitals, degenerate orbitals, are raising. Energy of the d orbital raised. Now, when the ligand has approached almost nearer, the degeneracy is lost. There is splitting of the orbitals basing on energy. So the dxy, dyz, dzx in the octahedral complex are gaining repulsion and the energy is reduced. These are getting stabilized. And these are not, and here the another set, Eg set, are split from the d orbital. The d orbital, one is T2G set, the other one is the Eg set. T2G set is the dxy, yz, and zx. It's getting lesser energy than the d orbitals, previous d orbital. And Eg set of d orbitals are gaining more energy compared to the previous d orbitals. So degeneracy is lost. These 5 have got split into Eg and T2G. Eg is gaining more energy, T2 is gaining less energy. So this is the difference in energy between the d orbitals, T2G and Eg set. Okay, so free metal ion, so much of energy has arisen. D orbital energy is so less, it has arisen so much. The T2G is here, they have split it, and Eg is here. Crystal field splitting energy. Now, effect of the ligand on splitting of energy. What is the effect of the ligand on splitting of energy? See, if it's weak ligand, high spin complex is formed. They get singly filled first for the weak field and high spin complex, chromium hexaphore complex. And if it is strong field ligand, the splitting has taken place and the occupying is for the strong field. First pairing takes place. Here completely single filling, not pairing. Here first pairing of the T2G takes place. after getting completed here and then it enters into EG. This is the low spin complex. See, if you see an artist's wheel, once if the complex absorbed at one particular radiation, another color is exhibited. You can see the observed and observed color, absorbed and observed color. How the relation you can easily see. Once if the absorbed color is violet, lambda 400 nanometers, then that is blue color 450 nanometers. See here, violet color it is 400 nanometers, and the observed color is green yellow. The complex will be green yellow. It will be emitting green yellow color that is being observed by us. That will be at 560 nanometers. If it is blue color at 450 nanometers, then observed color is yellow. You can see the observed color. That is the emitted color. So once whatever is absorbed, the emitted will be different. The observed color will be one and the emitted color will be different at different nanometers. If it is blue-green, 490 nanometers, and if it is red, and the emitted color will be red observed color at 620 nanometers. If yellow-green, 570 nanometers, and the observed color or the emitted color is violet and 410 nanometers. If it is yellow color absorbed at 580 nanometers, then the observed color is dark blue at 430 nanometers. And if absorbed color is orange at 600 nanometers, and the observed color is blue at 450 nanometers. If it is red color, absorbed color at 650 nanometers, the emitted and the observed color with the naked eye is green at 520 nanometers. Here. Violet color, green yellow. Violet color, you can see this green yellow. If it is blue, then it is yellow. If it is blue, then it is almost yellow orange. If it is blue green, then it is red. If it is blue green, then that can be red to orange. If it is yellow green, let's see violet color. If it is yellow green, then that can be violet color. Yellow green, then that is violet. If it is yellow, it is almost dark blue. Yellow, then it is almost dark blue. If it is orange, you can see blue color. If it is red color, you can see green. If it is red, you can see green color. So this is an artist's wheel which explains the observed color and the absorbed color and the observed color for complexes. Here you can see titanium hexaaqua complex. For titanium hexaaqua complex, it's almost very clear for us. You can see the absorption spectrum for this molecule. The absorption is at 400 nanometers started and its maximum at 500. It's reduced as the nanometer increases. Here these are the incoming radiations. In the titanium, you're having T2G1 electron. Okay. And this electron is jumping into EG. It is jumping into EG. Yeah, absorption takes place and it's jumping to the EG. And thereby you can see the color. You can see very clearly how the color. So many colors of the radiation in this visible region. Green yellow is observed, and almost you can see the color blue violet. If it's green yellow, if it is green yellow, violet color can be observed. Green and yellow, here the violet color is observed. Violet to blue. So this is the color. Basing on the observed colors, we can tell absorbed colors, you can give the observed colors. Now, effect of the metal oxidation state and the ligands on color. See, vanadium hexa aqua complex. This is the color. Vanadium hexa aqua class 3, the color has changed. Depending on this oxidation state, the colors are changing. Here the oxidation state of chromium is +3. Here the oxidation state is +2. Basing on this oxidation states, the color is changing. Yellow. Here you can see violet. Now, which is a strong field and weak field can be explained. Iodine. The strongest ligand is carbon monoxide, then cyanide, then nitrate, then ethylene diamine, then NH3, then FCN minus, water molecule, chloride, bromide. See here, the strong field ligand, it has large stabilization energy difference. It has shorter wavelength. Okay. If it is weak field ligand, it has less stabilization energy and longer wavelength. You see how it's getting occupied. These orbital occupancy for high and low spin complexes of D4 through D7 metal ions. Here, high spin weak field ligands. High spin, it is weak field. If it is low spin, it is strong. How you have to fill the electrons? See, for 1, 2, 3, 4 till D10, you can explain. Here, example D4 configuration. It's weak field, high spin complex. So the pairing takes place only after it's getting singly filled. First T2G is getting filled up with electrons and then EG. And if it is strong field, the 4 electrons, how they get filled up is first singly filled in T2G and pairing takes place in T2G. After completion of the T2G pairing, then it goes into the EG. Now D5 configuration, we see. In D5, you are having 5 electrons. Since it is a weak field, it's getting singly filled. Okay. And T2G and EG it happens. And if it is strong field, first T2G is getting singly filled and it's getting paired up. Yeah, this is strong field ligand. Coming to the D6 configuration, all the electrons are getting singly filled in the T2G set. After T2G set singly filling, then EG set is singly filled. And then after EG is singly filled, still one more electron is there. Therefore, that one electron is getting filled up in the T2G. So first, after single filling only, the pairing takes place. You can see in D6. Here, the pairing has taken place, the singly filling has taken place, and then pairing has taken place. But it does not enter into EG. So after single filling and pairing, if any electron is left, then it goes up. But in the weak field, single filling, after that, pairing takes place. EG, T2G, EG, and again pairing in the 2 orbitals. And in the D6 configuration also in the same way. Now coming to the D7 configuration. First, the 5 electrons got filled up singly. in the weak field. Then still two more electrons are there, then pairing takes place. First T2G and EG. In strong field, if you see, first T2G is getting singly filled, then paired up, and again electron is left over, that is to the EG. Here you can see tetrahedral complexes, how the electrons are there. You are having d orbitals dxy, dyz, dzyz, dz, xy, yz, xz. In xy, they are between the, or electrons are moving in between the coordinates. Xz also they are moving in between the coordinates. In yz also they are moving in between the coordinates. In z square they are along the axis. In x square, y square also they are along the axis. How it's taking place. Previously, I have explained you for octahedral complex how the splitting took place. Now, we'll see how the splitting takes place in the tetrahedral complex and octahedral complex. So, in the tetrahedral complex, once if you see here these electrons, the ligands are approaching between the axis. Here x-axis, y-axis and z-axis. They are approaching between the axis. And whatever orbitals are there between the axis are experiencing more repulsion. They are experiencing more repulsion. Thereby, the T2G set is the orbitals which are between the axis, and therefore they're between the axis, and therefore these are experiencing more repulsion. And once if the ligands are approaching, so tetrahedral complexes, the T2G set is experiencing more repulsion in tetrahedral complex. T2G experiencing more repulsion, and thereby the T2G set is going up here. It is getting splitted into, T2G set, and it is getting split into EG set. The T2G experienced more repulsion and it has gained more energy. Less stability. In EG set, d square x square and dz square, and in dz square, it is experiencing less repulsion, energy decreased, and it is stabilized. This is the way the energy difference has arisen between the two orbitals. Now we'll see this is the delta T. That is the delta T. Now, in the square planar complexes, the ligands are approaching along the axis. Slowly, energy of the d orbital has arisen. Energy of the d orbital has arisen, and thereby still the ligands are approaching along the axis. More energies, the energy difference, energy has risen, and still the ligands as the approach along the axis. So the ligands which are lying along the axis experience more repulsion, gain more energy, less stability. So d orbitals, they are split into EG and T2G. And EG orbitals, again there is further division. Similarly in T2G also, there is still further division. Okay, and thereby you can see here in T2G set, XZ and YZ have gained low energy, more stable, dxz and yz. And T2G and one more remain, that is Z square. It has come. And the planes, the ligands are approached along the x and y coordinates. So x, y, so you can see here, it's not at all along the z axis. So it is more stabilized, less repulsion. So how the T2G has splitted is xz and yz have come down completely, less repulsion for them. And in T2G again, there is splitting of xy to the about plane because the ligands are along the xy coordinate. Now, and the T2G set, whatever is there, it has got splitted in this way, and remained one is the EG set. In the EG set xy, the ligands are along the xy coordinates and it experienced more the x square y square d orbital dx square y square experienced more repulsion. It has experienced more repulsion and very less stability. Okay. High energy, more repulsion, high energy, least stable, x square y square. Then comes this dg square has gone completely down. Okay. T2G has split. Your T2G has split into two sets, dxyz and dzyz, and xy has gone up. And EG set dx square y square is up and dz square is almost up. This is the way the square planar has experienced the splitting of the orbitals. In the tetrahedral, we have seen the reverse. Octahedral, how we have seen is they're approaching between the axis and they're along the T2G has come down and EG has gone up. Now in tetrahedral, it's in the quite reverse way. EG has come down and T2G has gone. So the 5 degenerate orbitals lost their degeneracy. They split into two sets, T2G EG set, and octahedral T2G has come down and EG has gone up. In tetrahedral, EG has come down and T2G has gone up with more energy. In square planar complexes, the degeneracy of the d orbitals, first energy raised, then degeneracy is lost, again degeneracy is lost for suborbitals also. So d orbitals splitted first into T2G and EG, and again T2G has split into that. Again, the 3 orbitals got split up, and EG also further got split up. So this is the splitting pattern of the d orbitals based on their energy. Here you can see the free metal ion energy has raised and it has got split in the square planar complex. They are lying along the coordinate axis. The ligands have approached. So this is the way it has got split. Free metal ion complexes. Now the transition elements are they're having a lot of applications in the daily life. So transition metal atoms, the trace elements in humans, you can see. Some metal trace elements in the humans, for example, vanadium, the protein contain. The function is redox coupling in the fat metabolism. The chromium element, it is a glucose tolerance factor. Glucose utilization, this chromium is utilized. And coming to the manganese, isocitrate dehydrogenase enzyme contains manganese. And it is useful, this enzyme, for the cell respiration. Coming to the iron, hemoglobin and myoglobin, so they are present. This iron Fe is present in hemoglobin and myoglobin. And cytochrome C catalase also. So these are useful for the oxygen transport, cell respiration, ATP formation, decomposition of H2O. Coming to the cobalt, it is cobalamin, vitamin B12, and development of RBC. This cobalt is helpful for us. Coming to the copper, it is useful in the ceruloplasmin, cytochrome oxidase. It is useful for the hemoglobin synthesis and cell respiration and ATP formation. Now coming to the zinc, it is useful in the carbonic anhydrase. So, and carboxypeptidase A enzyme also contains zinc, which is the transition metal. Even the alcohol dehydrogenase enzyme contains zinc, transition metal. So, this is useful for the elimination of the carbon dioxide from the body, protein digestion, and metabolism of ethanol. And for metabolism of ethanol also, this zinc is useful. Next, you can see this tetrahedral zinc complexes in the carbonic anhydrase, how it's formed, the transition. Here, hemoglobin, you can see, iron, all these brown color ones are the iron atoms, how it's linking in the hemoglobin. Heme part, iron, okay, and porphyrin rings. Okay, pyrrole rings clubbed together, you get the porphyrin ring, and this porphyrin ring attaches with the iron and globin part of the protein. Oxyhemoglobin, how it's formed, you can see. So this is the wonderful chemistry, transition elements. So previous class, I have explained about the complex compounds, isomerism, the basic concepts. And today's class, the stereoisomerism 2, optical isomerism, how it's there in the octahedral complexes, tetrahedral complexes we've seen. And next, how the octahedral ions are bonding, how square planar are forming, how the tetrahedral are formed, we've seen. And basing on the crystal field theory, I've explained the octahedral complexes, square planar complexes, tetrahedral complexes, basing on their splitting patterns. And the color absorption is also explained for the different complexes. How for the weak field and the low, strong field, electrons are getting filled up, we have seen. And splitting patterns of the octahedral, tetrahedral, square planar is also explained. And we have seen the importance of the trace elements in the humans. Some of the examples were taken and explained to you. Thank you for today's class.